I myself learned quantum mechanics, something like 40 years ago, and I learned it from the Nobel Prize winner Norman Ramsey when I was an undergraduate student. And since then, I've pretty much immersed myself within the subtle intricacies and qualities of quantum mechanics really ever since. And when it comes to quantum computers, actually a real one that people are trying to make, I understand reasonably well, of course, the theoretical ideas underlying their operation. But if you came to me and tasked me with actually building a quantum computer, I assure you I would fail miserably. Now, in part, this is because in my particular physics upbringing, my training, I was so focused on theory, on the mathematics, that somehow I basically sidestepped just about every hands-on laboratory course. But even so, even if I did have some experimental training, there is an absolutely monumental challenge to translate the theoretical ideas of quantum mechanics into an actual computational device. Not animation, not visuals, but an actual device that can leverage the powerful but delicate qualities that quantum mechanics provides. Now, many companies are trying to do this, and some of these companies are claiming great success, that we are heading toward the day when quantum computers really will reach their potential. And our guest for this conversation is one of these intrepid scientists, and she's going to illuminate for us where things stand and how far we still need to go to realize that promised version of quantum computation. So I'm pleased to introduce Patty Lee, who is the Chief Scientist of Hardware Technology Development at Quantinuum, where she leads the team that is planning and en route to building a scalable trapped ion quantum computer. Patty. Thank you so much for being here, as I'd like to focus on taking the ideas of quantum mechanics and the ideas of quantum computation, actually turning it into a device that would carry out these processes. And so what I wanted to begin with is just some of the various approaches that people have tried and many are pursuing to build the quantum computer. And I gather the basic idea is you've got to find some physical structure that realizes this notion of the quantum bit, these bits that can be in a blend of, say, 0 and 1. And just as a kind of list of the various approaches that people have tried, together with the locations and the companies that have been involved, here's just sort of a sampling. Can you sort of just illuminate us, in just a minute or so for each, what it is that they are doing in these approaches? What are they building to try to create these quantum systems?
Yeah, so there are actually a lot of different objects that are quantum mechanical or have quantum mechanical behavior. And anything that has quantum mechanical behavior, you can pretty much make it into a qubit. And so a very popular one is the superconducting qubits. And so these are superconducting devices called Josephson junctions. They're pretty well known, and they have very quantized states that are, when you build the device, you can predict. And you use those quantized states, and you pick the two most lower energy state, usually, and you can use that for computation.
And they're sort of like your 0 and 1s, the lowest energy
That's right.
states.
And in some ways, a lot of these quantum objects have many, many different states, and as long as you can just pick two that are best for operation and entanglement, then assign that 0 and 1, and you can do your computation there.
And so that's for the superconducting case. If we move on to this other example, the one just underneath it, the neutral atom. Mm-hmm. What is that? How does that?
Neutral atoms, the same thing. So atoms have lots of different electron configurations. In high school chemistry, we learn all these different orbitals. Electrons have spins. And so again, you can pick usually a ground state levels for your computation. And you can use these atomic interactions, usually with these Rydberg interactions, so that when you put two atoms together, you can entangle them.
And is there a particular species of atom that people tend to focus on?
People typically like the group 1 atoms because it's all the electron structures look like hydrogen. So it's very simple, usually has a ground state, it's nice and clean, and we like the hydrogen atom because we know how it works.
How about the next here, photonics?
Mm-hmm. So photons are quantum mechanical objects, as you shown with the
little particles of light, right?
Yep. Yes, it's particles of light, but they have wave characteristics as well, and they will interfere with each other. Even just taking two photons and trying to interfere them, putting them through two double slits, you get interference pattern. And so they are perfectly valid quantum objects. And so you can assign either a 0 or 1 as there's photon or there's not a photon, or you can use a polarization, whether it's polarized vertically or horizontally as your qubit, or different properties of your photons.
And is that a fundamentally different way, or are they basically the same? In other words, when I think about neutral atoms or superconducting circuits, I think of them as being at a given location. When I think about photons, I'm hard-pressed to think about that photon is sitting still.
That's right. So that's the challenge with photons, is that now these photons, they're always going somewhere, and so you have to keep them going somewhere. You can't store them, like just hold them in place.
Unless you just chase after your quantum system.
And that's right. So sometimes you may have to put them into some fiber optics or some circuit where they just keep running around, and they're easy to lose. As they sometimes can get absorbed by the material. And so there are different ways of handling that, but you can definitely compute.
So there are a bunch of others, but I'd like to now really just jump ahead to the example that you actually use in your own work, which is this notion of trapped ions. So can we just drill down a little bit more on that and try to teach this theorist who never touched a piece of equipment what it actually takes in your particular case to create one of these systems that can carry out quantum computation? And I know that we have some visuals, but can you first give me the 30,000-foot overview so I can just get the idea, and then we can look at how you actually implement it?
Sure. So trapped ions really are, you just think of them as atoms with charge, right? So we take a neutral atom, a fine atom given to us by nature, and we remove an electron, and we have an ion. Sometimes you can remove extra electrons, but basically that system, atomic system, has its electron structures that are well known. You can characterize them, and every single one of them is identical, right? Because they're given to us by nature, all their atomic properties. And so they operate like
again, is there a particular atom again here that species?
Again, now we want the group 2 atoms for our trapped ions typically, so that once you remove an electron, that electron structure looks kind of like hydrogen. We like to keep it simple as physicists. It's the easiest way to operate, and so that's and the nice thing about these trapped ions is they're often naturally used for atomic clocks. Best atomic clocks are aluminum ion clocks, the same thing. And so these ions have very nice, very long coherence times naturally, and so it'll maintain that quantum memory for a long time as we do computation.
All right, so the basic picture then is starting to form. You have one of these group 2 atoms, you strip off an electron, you have this ion. I gather you're going to tell me now that it has charge, you can manipulate it more easily because you can use electromagnetic fields to do so. How should I think about the 0 or 1 structure here? Is it again excited states of this?
It's an electron excited state. So it's electron. So if you look at the electron structure, you get the ground S state manifold.
So the lowest energy state, that's like your 0 or something like that.
And usually there are these hyperfine splittings, as in the electron spin and the nuclear spin interact with each other. So you can find 2 states that are very stable. They're used for atomic clocks. And that's what you call, and you just label it 1 and 0. As long as you can manipulate it, and typically we do that with lasers. Sometimes you can do that with microwaves as well. And as long as you can control it, there's your qubit.
So let's then take a look at some graphics that will allow us to dig a little bit deeper. So tell us what we are seeing here.
Yeah, so this is a ion trap. You see those electrodes on the surface there. You apply both radio frequency and static voltages to those electrodes. So there you saw earlier with a neutral atom coming through literally a hole on the device itself.
Yep.
And we can strip out the electron using photoionization with a laser.
So you just
shine the laser,
zap it with a laser,
that's right.
kick out an electron.
That's right.
Now have this
Now we have a
ion.
charged particle.
Yep.
Now if we apply the right fields on those electrodes, right voltages on those electrodes, you generate the field that will capture the ion.
And so the yellow structure there that looks like it's containing the
That's
ion,
the potential.
that's the potential coming from this electromagnetic field that you have created, electric field, to hold it in place.
Yes, actually it's just electric field
Yep,
because
right.
these are charged particles. This
Yep.
is why neutral atoms, you can't capture it like that because
Yep.
there's no charge.
Right.
But with charge, it's easy to do that.
Okay, so that is step one, I gather.
Mm-hmm.
And then what are we seeing here?
So with these you can see there are lots of little electrodes on the ion trap. And so we can actually change the voltages on those electrodes and move these ions into different regions in the device. And there we just moved it into the laser, what we call the gate region, where we can shine the laser on it, on the ion, and then perform a quantum operation. So you can put it in a superposition of these, any arbitrary superposition you can define for this
So you can put
qubit.
that trapped ion in one of these superposed states and then allow it to start to carry out operations that are in this quantum domain, parallel computations of
That's
some
correct.
sort.
Yeah, you start out with putting a qubit in the superposition.
And a key thing is described in this graphic. So can you just take us through this?
So inside superposition, you need to actually entangle two qubits.
And just quickly remind us what entanglement is. I'm sure most people are familiar, but just a quick explanation.
Yeah, so when you have two different quantum objects, right, they may have their own quantum mechanical description, right, their own quantum state and quantum superposition, but they have to interact somehow so that when you entangle them, then all of a sudden their quantum mechanical state is dependent on each other. So this is some of the like a Bell state, where the qubit or your electron spin is always correlated. That is in form of entanglement. And so to do quantum computation, you have to be able to entangle your qubits, and you have to do it in a controllable manner so that you know you can actually form these massively entangled state using all of your qubits, so that when you're computing, you have that 2 to the n number of states.
And so can I think of it that, in essence, in the language of quantum computation, entanglement involves this profound sharing of the information between the members of an entangled state, so that they're no longer just acting independently, which is more what a classical kind of computation would do. This guy's doing his work, this guy's doing their work. Mm-hmm. What you want is them to be working together in some deeply enmeshed manner to leverage the full power of quantum mechanics. And that's what you do through these entanglements between the trapped ions.
That's right. And if you think about it classically, right, if you do a classical operation between two bits, right, they are dependent on each other during that operation, but then afterwards, when they go and operate with another bit, then those become sort of separate entities. In quantum computing, they're always entangled. As in, if once they're entangled, if I take one qubit and then go entangle with with a third qubit, that third qubit is also entangled with this first qubit that it has never met before, right? And so these are, that's how you get the power of quantum computing in that exponential sense compared to classical.
Compared to a classical system. Now, these are sort of nice visuals, animations that give us a feel for what's going on, but you actually have realized these states in an actual physical device.
Yes.
So what is it that we're seeing here?
So that is an ion trap. That is the structure, those electrodes that are holding the ions in place. And so that is a microfabricated device. You make these structures, and if you connect them up with the right voltage control, and like I described, you ionize the atom, and those ions can be moved around sort of above the surface of this device.
And so are there many ions that are influenced by this device, or is it one per ion? How does it work in terms of actually realizing it?
The device are just a bunch of electrodes.
Yep.
So they can hold as many ions as you're clever in designing your electric field
Yep.
that you can support those ions. And so this is an H1, this is actually our H1 system. It's currently holding 20 qubits. And users are programming it and moving these ions around and doing quantum computation with it.
Now, no doubt these are quite delicate quantum systems. So I gather, and I have an image here where you actually put these types of objects. So what are we seeing here?
Yeah, so you're looking at that device is actually inside an ultra-high vacuum chamber. And it's actually also under, it's in cryogenic temperature.
Can you give us a sense of scale? I mean, how big is this thing that we're...
The vacuum chamber is kind of like a football size. And so it just sits in the lab. The cryo system is not like the chandelier, but it's actually just flowing and cooling the device itself. It keeps the vacuum clean. So typically, our vacuum pressure is about 10 to the minus 12 torr. So these are really, really low vacuum. And the reason we want to operate under ultra-high vacuum is we don't want all these background gas and all these different molecules and atoms come in and knock those your nice clean qubits out of the trap.
And where is that device? I mean, is it sitting nearby? Are there many of those? I mean,
it's sitting in our lab right now,
like, where's
Colorado and Minnesota. Yep.
And is this the kind of thing where you have many of those and you're doing various experiments with each? Is this like a one of a kind?
We have many of those. So we have a few sort of what we call commercial quantum computers that we let users use. They're fully operational, can do all the computational operations needed. And we have several of those devices that people can access online. We also have a lot of test beds where we're testing out new devices and new ways of operating these quantum computers so we can build better and bigger quantum computers in the future.
Now, you mentioned that lasers are an important part of the ways in which, for instance, you can ionize these atoms and affect them in various ways. What are we looking at in this image here?
Yeah, so that's what is surrounding the vacuum chamber in our lab are a lot of optics and lasers. All of the quantum operations are actually driven by laser interaction with ions. And so these ions have these natural energy levels that are given to us by nature. We characterize them, and then now we have to go and build lasers that control these atomic transitions given those the wavelengths that are given, and so that's why you see a whole rainbow of colors. It spans from the infrared to the ultraviolet, through all the visible colors, because there are a lot of atomic transitions here. We use ytterbium ions, and so ytterbium ions do have some ultraviolet colors. And then there are also, we also have barium ions for what we call sympathetic cooling. That is to keep the ions around and so we can laser cool these systems while the ytterbium ions holding quantum qubits and quantum memory and performing the quantum computation.
So you tune the frequencies of these lasers based on your understanding of how these particular atoms respond to the presence of light, photons that interact with them, and that gives you presumably a precise set of tweezers to move them, a precise set of kicks to change their state, and that gives you the capacity to manipulate these with fantastic precision.
That's right. That's right. So I mean, we don't have the tweezers in the sense that tweezers are typically used for neutral atoms
Yep.
to hold their neutral atoms in place, because neutral atoms don't have a charge. So
Yes.
their handle is an optical tweezer.
Yeah, by the way, my tweezer reference is totally poetic, but I'm glad you interpret it literally.
But we do have these very sort of narrowed laser beams that hits the ions precisely. And yes, they are absolutely tuned to the transition, so they're driving exactly the coherent operations needed to perform these, entanglement and operations, or putting them in proper position.
And then when you put this into further practice, and I gather is this animation, or is this, what are we seeing here?
You're looking at actual ions, actual qubits running around in a device. So this is our H2 system. That looks like a racetrack.
And why racetrack shape? Is there a particular reason for that?
It's just a matter of how we pack them in and how we arrange the qubits. Right now, this H1, H2 are sort of more linear type of scale, linear systems, so that the ions are rotating or stored in this linear fashion. And you can see the ions are running around the racetrack in that video. That's an actual video of ions. We're seeing real qubits there. On the left is a device. You can see all the little electrodes on the device that control these ions. And so just by changing the voltages on those electrodes, we can make those ions move around.
And so how many qubits are we seeing involved in this?
So this device, the video you're seeing right there are 32 qubits. The thing is that number of qubits is not, it's really how we manipulate, how we control those electrodes. So this device is actually under beta testing right now for more than 50 qubits. What's interesting about more than 50 qubits is that it becomes the Hilbert space becomes so large that you can no longer simulate that, even with the most powerful supercomputer in the world.
So when you say Hilbert space, you're talking about the possible configurations in the quantum domain that these particles can be in. Is just so numerous that you don't even have the capacity to do a classical simulation because it's just too big.
Yeah. And so that's a really exciting regime, right? Because now we can actually do computation, at more than 50 qubits, when that's fully operational, that a supercomputer can't calculate.
And so this all sounds extremely promising, for the field. But if we can turn to some of the challenges that you're facing and actually implementing this in a manner that, I don't know if the goal one day is that everybody has a quantum computer on their laptop, but presumably the goal at some point would be that everybody who had an interesting problem that would be amenable to a solution with quantum computation would have a stable, large quantum computer out there somehow in the cloud that we could access. We're not there yet, presumably, but this is the direction that you're heading. And what are the things that you see as hurdles to realizing that vision? And I think there are typically a bunch of words that people throw at this: fault tolerance, decoherence, and so forth. Can you sort of take us through what these hurdles are and where you think we are in the journey to surmount them? Mm-hmm.
I would say the biggest challenge is actually driving down error rates, right? So these physical systems have errors that's coming from, some of it is physics, fundamental physics. A lot of it is in more instrumental environments that we just simply cannot control them.
I mean, just so concrete, when you talk about an error, you mean when you ultimately measure it, you wanted it to be a 0 and it's a 1, or so? I mean, is it that level of?
Yeah, but every operation, every entanglement operation, or
within the working of
within your circuit, introduces error, right? Because we can't do it perfectly. And so right now, for example, on our trapped ion system, we're able to get 99.9% fidelity. That means if you kind of want to think about it classically, we do a measurement, 1 out of 1,000 times you get a wrong answer, right? But of course, this is in sort of the quantum mechanical space, so it's a little bit different, but that's the idea, right? So there's always some limit, and I would say 99.9% is probably
that sounds
the best,
pretty good, right?
Best in industry right now.
Yeah. But I guess.
But it's not good enough because if you want, you want 100,000 operations in your computation, you can't get there. And so how do you get better? So obviously you can work on it on a physical level, but there's this concept of fault-tolerant quantum computing, which is taking a bunch of physical qubits to construct a logical qubit.
So I just want to understand, that seems to be a key idea in the field, because normally when we think about quantum computation, you think about each qubit as carrying the information that you want it to carry. But I gather you're saying that you can take many of these qubits to actually carry the information of one, and by having many, presumably you can have redundancies and you can have error correction built into it. And is that the way forward? Is that the way to minimize these issues associated with error? Yeah,
and I think classical computing does that all the time, right? When we're sending packets, and you write some your image on the CD or something, a lot of times bits gets lost, and there are ways to recover it, right? And so you can build that in, with redundancy. With quantum mechanics, it's a little trickier because there's no cloning theorem, so you can just straight copy it.
So just quickly tell people that the no cloning theorem, what does it tell us?
So if you have an arbitrary state, right, quantum state, you can't copy it. Right,
quantum mechanics forbids
that. Right, just the theory itself says you can't do it. Yeah. Right, and so you can entangle it, right, and create something that's an object that's related to it, but you can't copy it exactly, right? Then you can't just go measure that and preserve your original.
So redundancy, you have to be much more clever in the quantum realm, but people have found ways of being much more clever.
Yes, and there's this whole field of quantum error correction. Fault-tolerant quantum computing that describes how you encode logical qubits. There are many protocols to do that, and they apply in different ways. And so the idea is that once your physical error rate hits a threshold, if it's below a threshold, then you can just add more qubits to form these large logical qubits and get better and better error rates.
So what ratio are you dealing with now? How many of these qubits do you have encoding the information in this logical qubit?
Depends on how good you want the logical qubit error rate is.
Yeah, and where are you now?
Where are we right now? We just demonstrated with Microsoft just last month that we can get it to 800 times lower error rate by creating these Bell states using logical qubits. And the encoding rate is about 6 to 1 or 7 to 1.
6 or 7 of these physical ones to 1 logical one.
That's right. But it's very system dependent, right? If your error rates are higher in other systems, then you may need more qubits to even get to the same error rate.
But in the example you gave before, when you had, say, 50 qubits, should I then think about that more like 7 logical qubits because you need to build in this quantum redundancy?
So it depends on what kind of computation you want to use. If the error rates at those 50 qubits are enough for your computation, then go ahead, use the physical qubits, right? But if you need deeper circuits or better error rates than what the physical qubits can offer you, then you have to construct these logical qubits to get better performance. So but then your 50 qubits now becomes more like 7 or fewer logical qubits depending on the construct. Right, but it will give you better error rates.
And so when people talk about, when we have, whatever the number is, a few hundred qubits, the number of operations that will be happening is on par with, the number of particles in the observable universe, and therefore that's sort of, beyond anything that you could ever imagine requiring. We would really need to scale that up probably by some factor of 7, 8, 9, or 10, or whatever it is, to have this truly fault-tolerant version of that?
Possibly more. right, depends on how much error, what the error rates you need, right? If
Exactly,
you need
yeah.
it like a Shor's algorithm, you might need 10 to the minus 10 error rate. Then you need a lot more physical qubits to construct logical
Right.
qubits to reach that kind of error.
Now, when you mention that people can actually log on and make use of the system, what sort of interface does the system use? How does one talk to the quantum computer?
Yeah,
I mean, I'm from the old days. Last time I really did serious computing, it was with punch cards. So this is not really what that's a bit of an exaggeration. But, so how do you talk to it?
Yeah, so there are actually several programming languages, right, that people, that's available out there. We use what's called quantum assembly language, is what our quantum computers accept. But you can use other languages and use compilers to compile it to the proper, for the proper input for our systems. But the idea is it's just look like Python code, right?
Really?
Yes, you can use Jupyter Notebook, and there are standard, this is how you entangle, these two qubits.
Yeah.
This is how you put it in a superposition. You can define its, rotation angle and your gate operation, and you can define which qubits goes with where. You can define when the measurement happens. And in our system, you can even take the outcome of your qubit measurement and then change your programming. So it's like kind of like an if statement, and change your programming. So if it's 0, then you do this. If it's 1, you do something else.
And how many people make use of this?
We have hundreds of users around the world. And programming. So for example, the Microsoft demo, they're forming logical qubits. All they do is program lines of code. And our machine just runs it and produces that result. So you can even construct logical qubits using just programming lines of code. So it's very exciting because anybody, you can go and actually write program to generate these very exotic quantum states that has never existed in the world.
I'm definitely tempted to do this, and and no doubt will. So this is a hugely exciting. But I want to talk about one final piece of physics before we end, which is this other issue that goes under the name of decoherence, which of course is intimately related to a lot of what we've already spoken about. But when anyone hears about these qualities of the quantum world, superposition up and down, qubit 0 and 1, or entanglement, distant objects somehow sharing information, we all, I think, by this point have acquired the correct intuition that these are really delicate systems. And if you do anything to them, typically any kind of interaction, you are in danger of losing that pristine quantum quality which is required for the quantum computation to do what you want it to do.
It's worse than that. If you just leave it there, it will
by itself.
It will interact with its environment and
Yes.
decohere.
So what's the time scale in your quantum computer for maintaining that so-called quantum coherence, not allowing it to decohere into a more classical-like state?
So that depends on the system. So for trapped ions, for our system in
Yes.
particular, the coherence times is on the order of seconds. So maybe like 10 seconds or so, right? And there are other groups out there that have demonstrated, putting these ions in the system, and for half an hour they can maintain coherence.
But
Yes.
like in yours,
So-
when you say seconds, does that mean that whatever computation one does, in terms of computer time, it has to complete within a number of seconds, or else it just is going to fail?
If you're using physical qubits, that's true. If you're using logical qubits, the nice thing is that then you can go back and quantum error correct.
So you sort of re-cohere the system with your knowledge of where it was when it decohered?
Right, so the way quantum error correction works is that you have these ancilla qubits that goes in and do a syndrome check. So the trick is you have to check if an error occurs occurred in your system, in your logical qubit, without actually measuring your logical qubit.
Because if you measure it, then
it's gone.
you've destroyed it.
That's right, that's right. And so, but you can check and see, is the collective property, an error occurred, and then if an error occurs in one physical qubit, then you can go fix it, right?
Yeah.
And so that's what error correction does, and it extends that coherence time.
Right.
So yes, so our logical qubits has much longer coherence time than our physical qubits.
And so just for the final part of our conversation here, just to prognosticate a little bit, where do you see this going? I mean, presumably you're working on all these challenges to increase the coherence time, to decrease the error rate, and so forth. What is the end game?
Well, certainly, we want to be able to do these very complicated computation, right? But right now, I think the resources required for some of those really complicated computation or even Shor's algorithm, or quantum chemistry applications, those require a lot more qubits and a lot lower error rates than what we have today. But what we do have today is that we are already getting into this quantum advantage regime where we can run calculations that the largest supercomputers in the world cannot compute, right? Google had demonstrated it. There are groups in China that has demonstrated it. And our system, when it has 50 qubits, will be able to do that as well.
Maybe not up on the details, but I do remember some pushback from an initial announcement of so-called quantum supremacy, where there was a statement, we've finally done it. It would take a classical computer, 10,000 or a trillion years. I don't know what the statement was. And then others came along and said, well, actually, if you have a more clever algorithm on the classical computer, you can kind of do it in a couple days.
Right. So there's this thing in the classical computing is more of the techniques, right?
Yeah.
The techniques to simulate this gets better and better, and some of the tensor network methods, you can say, if people find clever techniques, they can do that, right? They can simulate it better.
Yeah.
But Google recently, this year, came out with a larger chip, right? And the thing is that if you have, just add 1 qubit, all of a sudden you have like twice as many possibilities. So the computing gets harder very quickly. And so they came up with a larger chip with a better error rate than before, and performed the same thing. And now that is guaranteed that the supercomputers cannot keep up.
Now, what sort of computation was used as this benchmark? Was it something?
Right now, it's random circuits. You randomly throw together this circuit and go, okay, quantum computer, you run it. How long did that take, and what's the answer? And then classical computer, supercomputer, can you compute that as well?
But right? When you say random circuit, is it a challenge that is in the sweet spot of a quantum computer to kind of, stack the deck in your favor, or is it really something that one would care about?
Right, so random circuit is more of a benchmark, right, to show that our quantum computers can do things that classical computers cannot.
Yeah.
But do you have a useful algorithm, right, a useful problem that can be encoded and fit onto that system and compute it in that regime? And right now, it's not clear, right, what that is. And I think that's where we need the theorists and we need the application engineers to go in and start programming and trying out and apply it to their application. So we're in this sort of middle regime where the known algorithms we know we can't get to, but we are better than classical computer. And so what's in that computation space that we can actually take advantage of? And that's where the sort of new research is, right? Because now we have a tool that had never existed before.
So if we were to have this conversation, say, at the World Science Festival in 10 years from now, no doubt I won't be in this chair. But if we had that conversation, do you think it will now be hands down that we have achieved quantum supremacy in a completely convincing manner, and that we are really leveraging the dream that these systems can do what they've promised us to do?
Yeah, I think so. And I would say that we are in that quantum advantage regime. It's just that we don't have the applications yet. Right. And in the next 10 years, it'll definitely get better. I think there are some of the I would say condensed matter physics applications and maybe some high energy physics simulations that I think are in that sort of 50 to 100 qubit regime, and in the near term, with error rates that we can reach in the near term, to be able to do those calculations that we can't do currently on classical computers.
Well, it's all very exciting, and I look forward to maybe having that conversation in 10 years. So thank you so much for explaining this all to us. Thank you.